Hello everyone. Today, my teammates and I are going to be discussing a paper on study on the influence of LED PN junction area on modulation bandwidth in visible light communication. The contents of this presentation are going to be background and introduction, which will cover the advantages of the components, experimental design and discussion, which will cover the experimental setup, measurements that are performed, results and simulations. Concluding this paper, we would be discussing what we have learned from the paper by implementing what we have learned in the class. Additional simulations and calculations will not be covered as per the time constraint. Let's go to background. What is LED? It is a semiconductor that emits light when current passes through it. What is VLC? VLC stands for visible light communication. As the name itself indicates, it uses visible light to carry information or communicate. It ranges from 380 to 740 nanometers. Why did the author choose gallium nitride? Because it has a high melting point and it is used in a wide range of electronic devices. The usage is predominantly increasing.
Gallium is doped with silicon or germanium for N-type semiconductor LEDs and doped with magnesium for P-type LEDs. Commercially available gallium nitride-based LED wafer has been used here. The aim of this project is the enhancement of the modulation bandwidth of LED through modifying the PN junction area in order to achieve better information transmission capacity. The reason blue light is considered because of its good reaction time and being much more efficient than the old-fashioned incandescent light bulbs. We focused on visible light communication because good amount of data can be transmitted with no limit of radio frequency, no electromagnetic interference in places of strong electromagnetic limits, and it's very safe and does not leak through buildings. Gallium nitride is used in this field because of its high efficiency, ability to be used for mass production, long operational lifetime, good compact form factor, no harmful emissions, that is low carbon footprint, and low maintenance cost.
The steps for fabrication of the gallium nitride-based LEDs are shown in these figures. First, the LED must have a mesa structure, which is used to avoid a sharp curvature of the positive P region next to the N layer, and periodic microvia holes made by etching ICP or inductively coupled plasma, which is a plasma source where energy is supplied by electric currents produced by electromagnetic induction. Next, the LED undergoes wafer cleaning by immersing the water into boiling aqua reagea, which is a mixture of hydrochloric and nitric acids and deionized water. Then the wafer is ultrasonically degreased by acetone, methanol, and deionized water. The final step in making the mesa structure and periodic microvia holes is lithography, where a pattern is transferred from a photomask to a substrate. After the mesa structure and periodic microvia holes is made, then nickel gold is evaporated by electron beam, then forms ohmic contacts on the positive part of the gallium nitride by rapid thermal annealing, which is used to change material properties. The chip is then passivated by plasma-enhanced chemical vapor deposition with silicon dioxide. Afterwards, the unnecessary silicon dioxide is removed from the positive part of the ohmic contact. Next, chromium, palladium, and gold are deposited, forming positive and negative electrode pads. Finally, the setup is flip chip bonded to ceramic substrate by micro solder balls. For our project, 3 different PN junction areas were considered: 200 by 800, 300 by 900, and 300 by 1,200 micrometers squared. Here's what we measured with the corresponding devices.
In this slide, we can see 4 different equipments that were described earlier in the circuit, and those were used to characterize the 3 different devices. And in this slide, we can see the electroluminescence spectra for the 3 different PN junction areas, and the same wavelength of 454 nanometers is shown in the figure to your left by all of the 3 different devices. And to the right, we can see the simulated result from the luminescence of this LED. The software that was used for this simulation was COMSOL Multiphysics 5.3a, and for this simulation, we considered a simplified model of the PN junction using the same material as the ones that were used in the paper. So the result of 2.9 electron volts were found from this simulation, and is converted to 427.5 or 428 nanometers, which is not significantly different from the experimental results and confirms the accuracy or acceptability of our model.
Hi, I'm Kishore. This is IV curve from both paper and from our simulation. From this curve, we see that operating voltage changes with PN junction area, and the operating voltage is maximum for smallest PN junction area and vice versa. And these are the curves for output power versus current. Normally, output power increases with increasing current. However, for small PN junction area, due to current overcrowding and low heat dissipation, the temperature in the junction will increase. As a result, efficiency decreases, so does the output power. And on the right side, this is a result from our simulations. Although we were not able to completely replicate the system, we were able to model some of the part from system, and still it is in compliance with the result from the paper.
These plots show the normalized frequency responses of the three sizes of LED at different currents. As you can see, as the applied current increases, the frequency response increases too. It happens because at higher current concentrations, carrier lifetime decreases and causes higher frequency response. We can also see it from simple ABC model at carrier lifetime, in which lifetime is inversely proportional to the N or the carrier concentration. This is the -3 decibel bandwidths of the different sizes LED. The capacitance curve of the three groups are also shown at the second plot, and the effective capacitance are red marked. Normally, the LED with larger paired junction area has the bigger capacitance and result in small bandwidth. LED 1 has the smallest area and its bandwidth are highest. But the interesting thing is that though LED 3 has the largest area, its bandwidth are not the smallest, rather higher than the LED 2. The reason may come from the capacitance. The effective capacitance of LED 3 is less than the LED 2. That causes higher bandwidth of the LED 3. Also, it can be inferred that capacitance is a key factor for -3 decibel modulation bandwidth in PLC. And we actually simulated the last plot, converting the RC equation to IVC equation and considering that IV and R are linearly related. As you can see, the outcome is a lot similar to the experimented one.
In this project, we studied the effect of different PN junction area on the performance of LED, especially for application of VLC. And we found out that normally optical power is directly proportional to input current. However, for smaller PN junction area, the optical power is not increasing as rapidly as the current increases because of excessive heating and less heat dissipation over the smaller PN junction area. And we also found out that there's strong relationship between LED PN junction area and operating voltage. We found out that operating voltage for smaller PN junction area is higher and vice versa. Hence, from our analysis, we conclude that optimal PN junction area is required for efficient VLC system. To conclude our project in a nutshell, in this project, we first understand the paper properly. We use the knowledge that we have learned from the class. We did calculations, and we also learned simulation, and we simulate some of our result, which was in compliance with the findings from the paper. Thank you.